Hello everyone, I am Dennis Wagelaar and I will present the ATL solution, ATL EMFTVM solution to the round trip case. I'm just going to start walking through the code. I'm going to start first with the initial solution that I did, which is the most straightforward to understand. So in ATL, basically what you have to do um, is you work with rules that will traverse the entire model and look for matching instances to transform. So this is exactly what I did here. So this is how you would solve task 1 with a normal ATL transformation. You have a regular matched rule here, which just traverses over all instances you feed into it and will transform it into other instances. So it will create a V2 person for every V1 person, and it will bind the properties of this V2 person as is listed here. Yes, so the name you just copy, and what you do here is here you use trace to find if you've already transformed the age before, um, or in case you haven't, you set it to a default -1. So the trace in this case is injected from the code, which I will show later. So the initial way you would run an ATL transformation from Java code would be like this. You have to set up your runtime environment. You have to set up an EMFTVM virtual machine, an instance. You have to create models because, well, ATL is a model transformation language, and in this case we're just trying to transform a single object. We still need to wrap that inside a model. We need the meta models as well. Here we have to set up the execution environment, which is actually the virtual machine instance we're going to create. We're going to register the meta models with it. We're going to load the module, which is this one, and then we're all set up to do the migration. So in this case, the tracing is very simplistic. The object that we're going to transform, we just store in a local field here, the trace field, and then when we want to migrate it back, we will just inject the trace into it. So the transform method here will take a trace. It will find inside the virtual machine the static field trace and will inject the value, set the value to the trace that we passed in here. So we can actually, from the code, set values of these helpers directly, and that's how we do the tracing directly in this case. Then we run the transformation and we get the first output element inside the model because we're just transforming a single object here. Okay, so this particular way of transforming has quite a lot of overhead because it will actually traverse the entire model, try to find the instance and then create another instance, put that in a model, then get that back out of the model, and then you have your output. So there's a faster way of doing this, and that is by actually directly invoking a given rule. Here we will simply look up the rule that we're going to use. So it's every time, because we're transforming a single object, it's a single rule. We get the first rule. We match it manually against the instance that is provided. So here we don't actually have to look up the instance. We're just going to provide it directly and then match it. And we will return the result of applying that rule. So now we skip the whole step of traversing a model. We just apply a rule directly to a certain input object. The regular way of running EMFTVM does not support this. So in order to make this work, we had to provide a special implementation. Yeah, there we are. So the manual execution environment is slightly different because it has a run and a post run. We don't want to do the actual run here, we just do match manual, and therefore we need to do the post run. And the post run is very important to do the cleanup afterwards. If you don't do the cleanup, you will actually get a memory leak. So therefore we have to provide this post run in order to do cleanup. It's actually not such a big adaptation if you look at the original implementation of the execution environment, which is much bigger. So if you go for run here, then you will see this same cleanup here and the code here. So basically what I did is I cut the cleanup bit out of the run method and I put it in a separate method. There's a slight difference between how the tasks now look. So this is the original version, and this is the current version that I'm running. Instead of using a regular matched rule, I'm now using a lazy rule, and the lazy rule is basically suitable for invoking manually. Every transformation is then made up out of a migrate rule. The back version will do the reverse transformation, and it has a migrate back lazy rule inside it, which just performs the reverse step. Common helpers contains the trace helper attribute, which we can set from the Java code. And it also has a year attribute, and the year, here we have to set a birth year, and we basically do this by taking the current year and deducting the age. So then we need to get the current year. This is not, of course, a built-in function for ATL, so we actually have to access a native Java class, and in this case a static operation, where we call getInstance on Java util calendar, and we basically call get1, and 1 is a code for getting the year part of a calendar instance. So this will return us from the Java world the year as an integer. This is for when you want to have null support, basically being able to set a name either to an empty string or to OCL undefined, which is the null in Java. So here you can distinguish between being undefined and being an empty string in ATL and pick one of the two. Task 4 was transforming a composite object. So here we have a container that we're going to transform in this case, and it's not only a person but also a dog. So the migrate rule we're still going to invoke with our top level object, but then we're going to traverse into the contained objects by taking the matched instance here and taking the dog out of it and taking the person out of it and invoking other lazy rules. Dog is fairly simple. It will instantiate the v2 dog, but person is a bit particular. We're using a unique lazy rule for person. Why do we do this? Because we are invoking the person rule twice on the same person. So here it's instance.person, here it's dog.owner, and in case these both point to the same person, we don't want to create two persons out of it. So what does a unique lazy rule do? For every unique person in, you will get a unique person out. I also did a run of the performance, and I've managed to plot out the ATL solution that I've built here against the reference solution. First of all, you can see that both of them scale linearly. It's just that, of course, the Java solution is still a lot faster. So it will run the largest model, that's 2 million repetitions here, in about 50 seconds. If you do the same thing in ATL, you will come above 250 seconds. So that is 5 times slower about. So there's still quite a bit of overhead of that you will pay for instantiating the ATL machinery. Okay, so that's about what I have to say about it. So I hope this was informative and you enjoyed it, and I hope you can compare this to what you guys have created. And yeah, I wish you guys good luck in the contest, and hopefully see you next time. Goodbye, everyone.